Good evening. So here we are for part 2 of lesson 15 of CENG 4412 Steel and Concrete Design. Alright, so in this video what I want to discuss is the topic of development length or bond length for steel in reinforced concrete beams, or actually in really any sort of reinforced concrete structure, but we're going to talk about development length specifically for the case of beams. So development length. Let's look at this. Let's introduce the concept here. So the whole idea here with development length is that, or whole idea with bond stress is that steel fundamentally, if I look at rebar, let's say I want to look at rebar bond stresses. Rebar bond stresses. Well, we know that in any kind of beam, for example, we're going to have both compression and tension present in the member. So if you're looking at a reinforced concrete beam, say some beam here, and this is your beam, and if we're considering this as positive bending, so we have our rebar here, well, you would have compression at the top in the Whitney stress block and tension on the bottom in the steel. So compression up here in the Whitney stress block and tension down here in the steel. Now, mechanically though, how is this going to work? How is that in order to actually transfer stress between here and here, or in other words, one of the assumptions that we learned previously when we learned about the theory of reinforced concrete beams, is sort of our standard bending assumptions. And one of those is this kind of thing here, where if we have our epsilon, if this is strain, epsilon, we have a kind of linear relationship between strain and depth. And so in turn, what we're assuming is, remember, we make the assumption in all beam theory usually that plane sections remain plane. Plane sections remain plane. This is one of our core assumptions in most elastic beam theory, and plastic as well. Remain plane. So we are always assuming that plane sections remain plane. Now, I don't know if you remember that, but whenever you look at any kind of beam theory or any video I put together on beam theory, and if you look in any text, etc., that's always listed as one of the assumptions of beam theory. Or in other words, if you imagine, if you're not familiar with what that means, if you imagine a beam made of many, 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 many layers. When you put that beam into bending, the individual layers they may each bend, each individual layer may bend, but the actual order and distance between each plane doesn't really change. It's just the whole thing bends together in one arc, while each plane still remaining the same distance between each of its, the one at the top and the one at the bottom, or one below it and the one above it. Okay, well, that's a really bad arc. Something more like that would be better. Okay, so we have that, but in order for this to happen, in order for plane sections to remain plane, things have to remain bonded together. Things must remain bonded together. Or I should say, in order for this to be true, subsequent layers must remain bonded together. Subsequent layers must remain bonded together. Layers must be able to bond. Or, in particular, in the case of steel in concrete, the steel needs to be able to actually grip the concrete. It needs to be able to grip the concrete and transfer stress. It must be able to grip the concrete and transfer stress. So, what do I mean by this? Well, consider this for a moment. Let's say I wanted to pull on a piece of rebar strong enough that would actually break. So let's say I wanted to take a piece of rebar and pull on it really with a force equal to maybe its ultimate force, which would be maybe Fy times the area of steel, not ignoring any kind of strain hardening, that sort of thing. let's say I want to have maybe I could idealize this as a fixed support or something. Let's say I want to pull on a piece of steel, and I want to pull, I want to see, basically I want to be able to pull on this piece of steel right up to the limit of its strength. And really that's what we're doing when we're doing concrete beam design. That's our standard assumption when we assume that, say, steel yields, as we saw in our first look at concrete beam bending. Well, let's look at this fixed support here, though. If I want to actually do that, I need some way of retaining this piece of steel here from deforming, from moving at the left end. And let's say this fixed support consisted of a chunk of concrete. Say this was a chunk of concrete in which my steel rebar was embedded. Something like this. Oh, I missed my support disappeared on me. So maybe a chunk of concrete that the steel was embedded within. Well, the question is then, how much concrete, or how much concrete am I going to need in order to actually successfully grip this? So, for example, let's look at one extreme case. Let's say I were to just barely put this piece of steel inside this concrete. Let's say I would only put, I don't know, like 1/16 of an inch or something incredibly small like that. Well, there is no way that tiny bit of concrete, it'll have some bond, but it'll be so low that there is no way that tiny bit of concrete is going to be able to sufficiently grip the steel. Or in the other extreme, so obviously a length of, an embedment length of, so let's talk about embedment length here, or embedding length, or embedded length. And this is not values you'll see in the code or anything. This is just me playing with numbers. Obviously, 1/16 of an inch is way too little if I want to develop the full strength of the rebar. Way too small. But then something like, oh, I don't know, let's pick a really high value, like, I don't know, 10 feet, 100 feet, a quarter mile. Yeah, let's go with that. 1/4 mile. Obviously, if I have a quarter mile of concrete, there is no way that will not be able to develop the full strength of the rebar. Or if you don't think that number is ridiculous enough, pick a mile or 10 miles or whatever ridiculous thing you want to pick. This is obviously going to be sufficient to fully develop the strength of the rebar. So in other words, past a certain point, once I embed this long enough, once I embed this piece of rebar in enough concrete, it won't be the bond at the surface that is breaking, it'll be the rebar itself. And so that concept that we're looking at is called development length. Development length is basically, when we say development length, what we're talking about is the length of steel, or the length needed. The length that a piece of rebar needs to be embedded within concrete in order to fully transfer its stresses. The development length, actually let me say just development length here. If I define development length, what does this mean? Let me do it over here. If I were to define development length, give a nice definition of this. Development length is the length or distance that a piece of rebar must be surrounded by concrete in order to fully transfer its stresses. That a rebar or other steel, actually, other reinforcement, or so let me say reinforcement, that reinforcement must be embedded in concrete in order to fully transfer its stresses. In order to fully transfer its stresses. Transfer its stresses. So let's try to figure out how we can determine this. So I just want to define it first, but then I want to look at it from the point of view of stress theory. So let's say we want to transfer stresses, and let's look at this again from the point of view of rebar bond stress. So if I look at just the bar here, there are going to be two different stresses present, or a balance of two things present. There's going to be, and let's say at the end of a beam here, there's going to be two different stresses present. One, there'll be the actual internal tension present at the end of the cross section. That's our T that we refer to usually. Our T load, our actual tension in the rebar, And then for any given point of any given section of rebar, we'll also have this kind of skin friction. And this is the frictional force that is resulting from the concrete gripping the steel, gripping the rebar. So we have this sort of skin friction effect. And especially with the formed bar where you have the ridges and such on it, not smooth bar, concrete does grip the steel quite strongly. But then also, let me say, I would also like to look at this from the point of view of maybe not something at the end, but maybe something like a certain DL, like a change in length, a small differential element. If I were to look at something like that, a small differential element, let's say maybe this would be, let's say, at the end of a bar. But maybe here would be towards the middle of a bar. Middle of a bar. So here on this one, we don't have, at the end of the bar, we're not going to have tension on the left end because that's just the end of the bar. It's the end of the beam, that sort of thing. But in the middle of the bar, we would have something like this. So you would have I'm going to draw this sort of pseudo 3D. Oh, not like that, maybe more like this. Nice straight bar. Nice perfectly drawn line. And then let me label this maybe end 1 and end 2. And in turn, maybe we would have FS1 and FS2. These are going to be lowercase f's. So here. So this would be maybe here. FS2, that would be the stress in the steel at end 2 times area 2. Or maybe just times area of the bar. It's the same bar, so just times AB. And maybe this would be FS1 times area of the bar. So if we had a differential element, it is possible that we would have different stresses, different tensions at either end, and then some sort of stress in the middle, distributing and connecting with the concrete. Something like this here. And this whole thing, then across this, there may be some average stress, mu. Mu would be the bond stress. The bond stress. And so let's apply some equilibrium equations. I want to apply equilibrium to this. So there's some bond stress mu applied, or some average bond stress mu applied over the cylinder here. Then I have a stress on one end, a stress on the other end, and multiplied by the appropriate bar strength, bar diameter, or bar area. So let's apply equilibrium to this. I'd like to get a title here. So let's apply a title. And so next apply equilibrium, I should say, to this bar here. So if I apply equilibrium to this, just simple statics or mechanics of materials equilibrium, I would get an equation like this. I would have the F of steel 1. So FS1, that's the stress on end 1, FS1 times the area of the bar, plus pi, this is just going to be the area, this is what I'm going to have a bond stress, and I'm going to multiply by the outer area of a cylinder. Pi times the diameter of the bar, so that's the circumference, multiplied by the length, so that will give me the outer surface area of the cylinder, and then times my mu average. And then this would have to equal FS2 times AB. Times AB. Times AB. And then what else? So, and in terms of what AB is just going to be the cross-sectional area of the bar. So that would be pi times dB squared over 4, the diameter of the bar squared over 4. And then, and I'll also later introduce something called delta F, but I'll come back to that. So then if I wanted to, I could put this, let me move this over here. And so pi here, pi times the diameter of the bar times L times mu average, it's a really messy mu, the Greek letter mu average, is equal to area of the bar times the difference in stresses, FS1 minus FS2. Or I guess actually in this case, FS2 minus FS1. Minus FS1, and here delta, and then let me next define delta F, which would be the change in stress along one length of a piece of rebar. And so this would maybe mean FS1, again, FS2 minus FS1. Or here, if I then put this in for here, let me put in delta F this and replace area of the bar with this expression here. So pi dB L mu average equals pi dB squared over 4 times delta F. And in turn, the dB and the pi will cancel out and the square will go away. And I would end up with an expression that the average stress, the average skin friction stress, the average bond stress, is equal to delta F, whatever the actual change in stress is there, delta F times dB divided by 4L, divided by 4L, 4 times the actual length of that member, or that element, 4L. And at first it seems like we could use this to directly calculate some sort of bond length. The difficulty, of course, is that then this is just looking at only the bond stress, figuring out what kind of stress is needed to on average, equal the same force as the yield strength of the material. But we don't really know anything about the strength of the concrete around this thing yet, so things are going to get quite a bit more complicated. And we don't necessarily know the actual change in stress. We actually just sort of know a change in F over L, et cetera, et cetera. But this is just one thing we can consider going forward. So next, I next want to look at how steel and concrete interact with bond stress. In particular, once you have a member that's actually an element that's actually cracked. So we know, of course, that at least in tension areas, that concrete will be cracked, much like yourself after maybe getting through this course, or maybe right now even. So steel, concrete, I made a crack joke. Steel, concrete, and bond stress and bond stresses. So here, now let me draw a sort of a piece of steel. Imagine me drawing a piece of steel that joins together, or consider, let me just label this maybe. Consider a piece of rebar in the tension zone. In the tension zone. Where, in the tension zone where the concrete is cracked. So effectively when this occurs, the steel ends up joining together separate pieces of broken concrete or cracked concrete. It ends up bridging the gap between cracks where concrete is cracked. So here, let me draw out a show a few chunks of concrete, something like this, and maybe I had another matching one over here, kind of like this. I'm just going to draw some shapes and kind of try to make them match up a little bit, something like this. And maybe the exact shape doesn't really matter. I'm just trying to illustrate the fact that this kind of cracks unevenly, and I could have adjacent pieces that kind of go together. And then bridging these would be a piece of rebar, so connecting these. And this would, of course, extend higher than this, but and the tension crack wouldn't go all the way to the top. You'd have this is just a small piece of my overall depth of my beam, because obviously up the top, you would end up up in the compression zone, you would have actual concrete bearing, concrete bearing against concrete. So maybe let's do a little bit darker blue here. Maybe this. So the steel then would end up bridging between each individual piece. So the steel is going to bridge between each piece here. Same thing here, same thing here, and extending out beyond this one. And here. And then applied to each end of this, I would have my point load P Oh, let me show that this is continuing through. It doesn't stop, it just is not visible when it's embedded within the concrete. Here. And then maybe I have some load P applied. I have the actual tension load in the steel, maybe a P, or actually for consistency, maybe I'll say this is T and T, the tension. Okay, so let's look then at the actual stress in the steel. Let's look at the stress present in the steel. So the stress in the steel is not because of this concrete starting, concrete stopping, concrete starting, concrete stopping. The stress in the steel is in turn not going to be uniform. See, every time the steel interacts with a new piece of concrete, it's going to undergo a change in stress. So this is going to be the steel stress here. And actually, let me draw this a little bit higher because I need to squeeze a few things into this page. So the steel stress would be up here maybe. So this is steel stress. And it's going to be mostly uniform, but it's going to go down every time it passes through one of those chunks of concrete, where it starts shedding some of the load into pieces of concrete. So uniform, then it dips down a bit. Uniform, then it dips down a bit. Uniform, uniform, then it dips down a bit. Well, that's just really bad. Let me just start over on that. Okay, so uniform, then it dips down a bit. Uniform, then it dips down a bit. Uniform, then it dips down a bit. Then back to its old value. Uniform, then it dips down a bit, and then it ends back at the other end of the beam. And then so this actual uniform level is what we refer to as our Fs. Fs, the stress of the steel, and that would be equal to tension, the T, divided by the cross-sectional area, A of steel, As. But then in turn, the concrete is going to have its own stress. Concrete's going to have its own stress, and it's going to be like this. Every time a piece of concrete, because again, the steel needs to be able to transfer load and transfer deformation back and forth between the compression zone of the compressive concrete, which is up here. And the only way it can do that is by transferring some stress into each individual chunk here. And so in turn, the concrete will also have some stresses. And it would be kind of like this. It would be, well, this is concrete stresses. It's not going to have very large stress, but it is going to have a small amount of stress as it's developing the load each time. So it's going to go like this, it's going to increase and then go back to zero, increase and go back to zero, increase and go back to zero, increase and go back to zero. Basically, it's going to fill the holes up in our steel stress here. And in turn, then we would have some, and this is equal to the FC, the stress in the concrete at some point. But in turn, we also have our bond stresses, and the bond stresses basically represent it's the friction bond, the stress needed to transfer, to make this go higher and then lower in the concrete, basically. Make the stress go increase and then decrease as we go from one end of a chunk to the next. So bond stresses would be positive and then negative, or negative and then positive. So bond stress would be something kind of like this. Positive then negative, positive then negative, positive then negative, positive then negative. Or in other words, on any given piece of concrete, the average bond stress is actually zero. Basically, at the end of one chunk, there's no bond stress, and the other chunk, there is no bond stress. And whatever stress is going to be distributed has to be equalized if this thing's going to remain in equilibrium. So overall, average bond stress on a given embedded piece of steel is going to be zero. But this is just covering some theory. Average bond stress is zero. On a chunk of concrete is zero. A piece of concrete is zero. Is zero. In other words, Or in other words, the tension carry doesn't change. Does not change, and that makes sense. Doesn't change. If I can squeeze the word change in here. Doesn't change. So we have that, and then let's next look at how this interacts with a cracked beam. So overall stresses in a cracked beam. How this interacts with that. Stresses in a cracked beam. The stresses in a cracked beam. Well, so here. And anyway, keep jumping ahead. Stresses in a cracked beam. Well, let's say you had a simply supported beam. I don't want the highlighter. Let's say I want the pen. Let's say I had a cracked beam, or sorry, a beam that was simply supported with a couple point loads on it. So something like this. And I have a couple point loads on here. Maybe one here, and one here with reactions here and here. And then let's say I have cracking like this. Something kind of like this. Here, 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 maybe like there. And the actual moment present in the beam would be something like this. If we look at the moment in the beam, the moment, it would be something kind of like this. And without any kind of cracking effect, you'd expect the stress, the maximum stress at any given position to also behave like this, kind of a trapezoidal moment distribution. But because of the this increase and decrease in stress between cracked sections, you would actually get a steel stress that would look something more like this. The real stress in the steel would be slightly more complicated because of the development lengths and stress concentrations, etc. Okay, so this would be the actual steel stresses. The actual steel stresses would be something more like this. They would still follow the overall general shape here, but they'd almost be like a sort of up and down funny tilt-a-whirl version of this, where every time there's a crack in the steel, or sorry, crack in the concrete, you're going to get an up and down, and this is the up and down is probably exaggerated here. But you're going to get that kind of, on average, it will behave like this, but you're going to have, so on average, yes, it does do this kind of thing here, but in reality, it's going to have some of that up and down behavior that we discussed previously. And that's at least, so that's one complication of how, if we're looking at the bond strength, in order to carry a required tension load, that's the actual stress that would be present, and so that would need to figure into any kind of calculation of development length. But also, not only do we have, if we're looking at development length, not only do we have to worry about this kind of stress in the steel, we also have to worry about splitting around bars. So not only do we have to worry about the steel failing, so obviously we're not worried. One limit on our development length is, okay, what's the maximum amount of stress the steel is going to experience? So our development length must be enough to carry that. But then another limitation on development length, it must have enough length not to break the concrete that's around the steel. So splitting around bars effectively. So in other words, if you have a, I'm going to draw a few things. Basically concrete around a piece of rebar. Not only can the steel itself have, not only does the steel itself have an upper limit in strength, but the concrete around a piece of steel will have an upper limit in strength. And so here, there's a few limits on this. One will be based on the minimum edge distances permitted, or the minimum edge distance to concrete surface or other bars. Minimum edge distance, and you can get basically you can get splitting sort of failure planes along these minimum edge distances. So you can get a failure plane that's sort of like almost like a block shear failure like you would have in steel design, And this is just so based on whatever the minimum distance is, etc., you can almost get like a block shear type failure where concrete would just pull out like that, like it would with steel. Minimum edge distances to concrete surface or to other bars. So this would be one form of splitting that could occur, or other bars. And there are a few things we could look at. Let me just illustrate a few types of this. If I have two pieces of rebar here, and I'm going to draw a few of them, three different sort of failure modes that we could have. Here, here, and then maybe here, here. And I'll draw three different types of failure modes and then sort of the effective concrete diameter that we're pulling out for each of these. So we could end up with we could have an edge, we'll have edge slash or bar to bar, edge or bar to bar, or bar to bar. We could have side or bottom, or we could just have a pure bottom failure. So in that case, you could have something like, let me show the failure plane. Maybe the failure plane here would just go across the surface like this. Here, maybe the corners would tear out, something like this. And here, maybe you just get a chunk failure like this pulling out just here. Something like that. So you can get failures like this, and you would, if you wanted to use a pure mechanics materials approach, you'd have to calculate the stress of each of these, the capacity of each of these failure modes, just like we do kind of with steel. Then you also have to take into account tensile failure, the tensile strength of concrete, where the concrete just fails in tension. Tensile strength, or I should say tensile strength of the concrete and the steel together. And three, we also have to worry about what exactly is this average bond strength. What is the say the bond strength that concrete cement paste can withstand? What is the strength of that bond? So looking at all of this, we can see that actually predicting the bond strength of steel, or the development length of steel in concrete, is incredibly difficult. We have to worry about the exact minutia of stress distributions. We have to worry about cracking. We have to worry about various edge cases where how the concrete can separate from the steel, how the concrete can fail in tension, the actual strength of hydrated cement paste. Oh my God, I want to scream. This is just way too much. This is too complicated. This doesn't work. And this doesn't mean that I'm just giving up and going home, but this is not going to work. This is making me sad. So we can't do this. That's a really bad me. There, and you learn the most interesting things in my class. This makes me sad. Too complicated, not very useful for design. Not useful for design. Anything with that many factors on it is not going to be something that we can rely on to safely design structures. So we need another way to do this. So another way we can do this is, we can go back here. And so we need another way forward. And really this is really what the concept of development length is. So I kind of alluded to this earlier, but trying to predict the actual length needed for a given load is usually too much. So usually we won't go and say, okay, well, we don't operate on the principle of, okay, well, what is the, we don't say, okay, well, what is the actual load present, and then make sure we have at least that much development length. Instead, we just design everything for the maximum. And the lengths are actually reasonable enough that this isn't a problem, so we can get away with this. But we need a way forward, and the way is like this. A way forward. And the way we're going to handle this is that we're going to find the shortest distance, and this is really what the ACI code uses as well. Look at the shortest distance Needed, necessary to develop stress in a bar. That's not how you spell necessary. Necessary to develop stress from zero all the way to Fy. To the yield stress. And this length is what we refer to as development length. We're going to find this, and then we're just going to say, okay, well, whenever there's any kind of transfer of load, we're going to make sure we have at least that much development length. We want to make sure we have at least that much. And that is the concept of development length. So here, and here, using the previous equation that we saw, the equilibrium-based equation, well, using the previous equation, you would get, if we let, for example, if we let delta F, the change in stress, be equal to the yield stress, and rearrange, you would get something that LD, development length, is equal to Fy times dB, the diameter of the bar, divided by 4 times mu average ultimate. Mu average ultimate. Where this, the mu average ultimate, this is mu average ultimate. This is the value, the average value, average ultimate value of the bond failure. Stress, anyway. Let's see, average ultimate bond failure stress. Now, if you look in the the concrete manual or the ACI code, you won't actually find this equation, but this is really the theory that this is based on. Basically, this is the theory that it's based on, and then we have a whole bunch of other terms that are included to take into account all sorts of other cases and things like that. All sorts of other applications and specifications and specific things, etc. So I think I might stop it here and just call this portion of the lecture the theory of development length, and then I'll do a part 3 where I look at the code of development length. All right, that'll do it. And thank you for watching, and we will be back.